This is the second iteration and a complete rebuild of my autonomous boat project called Gumption Trap II. It's mainly going to be used for creating depth plots of small freshwater lakes and ponds. And a quick overview of it before I get into the building process, design, and the internals. It has two solar panels, each nominally 100 watts. It steers primarily with this dual rudder system, and it's also capable of differential thrust between the two motors. Between the two hulls down there is the sonar module, and up at the top of the mast is the GPS antenna, manual mode transmitter antenna, and a camera. I mainly designed it around these solar panels. In total, it's about 6 foot long by 3 foot wide, and I kept it just small enough to fit in my truck bed. It weighs about 65 pounds, and I have it on top of this wheeled little trailer to move it around. It has an internal compass in one of the hulls, and combined with the GPS data, it's able to autonomously steer around following a predetermined path on a set of coordinates stored in an SD card inside. For scale, here's the previous version sitting on top, and the main flaw with that one was just that it wasn't powerful enough to overcome winds and strong currents. So I upgraded the solar panel significantly and mostly designed the rest of the boat around that. I modeled pretty much the entire assembly before I started building anything, not necessarily down to every last nut and bolt, but all of the important stuff, in particular the hulls. This is one hull assembly. I went with a dual hull design because I think it lends itself well to having a large flat solar panel on top, and these are made of fiberglass to keep it as light as possible and being fairly easy to make this custom shape. It's a plywood deck bolted down on top with a sealed gasket between the two. In the back, I have the motors mounted on one piece of laser cut stainless, and that bolts onto this other bent sheet metal assembly. The first part is embedded into the fiberglass so that it's structural and secure, and the other part is bolted on so that I could iterate it and change it as needed, and that secures the motor and the rudder assembly. To do some buoyancy analysis, I modeled a solid shape of each pontoon with the density of water. So that lets me quickly determine the displacement of 65 pounds is what I modeled it for. And the reason I did that is to have a safety factor of 2, meaning that if one of the two hulls totally floods, the other will still provide enough buoyancy to keep the boat afloat. So that would be a mission failure, but it would at least be recoverable. It wouldn't sink if one totally flooded. While designing this to predict where the water line would sit when the boat is afloat, I can cut off the portion that I expect to be above the water line and then reevaluate the weight of the water it displaces. In this case, if the water line's there, it would be about 30 pounds of water underwater. So times 2 hulls, that would be roughly 60 pounds. So 60 pounds of buoyancy equaling 60 pounds of weight, the water line would sit right there. So I kind of tweaked that and tweaked the geometry as I was designing this to settle upon my final cross section for the hull. I wanted to minimize the frontal area of the portion that's underwater to keep the drag as low as possible. So that's why it's very long and skinny, also to have enough room for the solar panel on top. And secondly, I also needed the draft to be deep enough that I could at least have the full propeller securely under the water and a strong mounting point for it. The mounting plate for the propeller sticks a little bit below the rest of the hull, the water line being about here where this transition period is. As I get above the water line, I wanted to minimize the actually side area so that it wouldn't be as affected by the wind. It wouldn't act like a giant sail if I just kept it being skinny and sticking further above the water while maintaining enough displacement for at least a 2x safety factor. And then I just kind of rounded off the bow and gave a flat attachment point for this plate in the end there. I used the same model to create this mold. With the geometry, I was keeping in mind that I had to build this out of fiberglass, so I tried to keep a lot of flat faces to make it easier to create the mold and lay the glass. and I 3D printed these end sections and these middle supports, and then the rest of the main body of the mold was cut pieces of plywood that were glued to it. And I also 3D printed the round sections and glued all the printed parts together to form this mold. And where the butt ends of these plywood panels come together and any other little gaps here and there, I just used some fairing compound to smooth it over before I laid down any fiberglass. This was my first time working with fiberglass, and consequently the first hull did not turn out nearly as well as the second. I learned some tricks along the way that made it much better. I laid some tape across the mold and sprayed mold release on it, which was a lot better than the first time when I just used a loose sheet of plastic that led to a bunch of trapped air and bubbles. It helped a lot to do the entire thing in one section rather than lots of small parts, because I ended up with some leaks where the small sections overlapped. And I did use the same mold for both, but the second one I kind of destroyed it in the process of releasing it, because I actually forgot to apply the mold release to a few sections, and it got so stuck that it just became destroyed. And there's the tape that I used on top of the plywood. The next problem I ran into is that the top surfaces, the mating surfaces, this fiberglass, they definitely turned out, this is the worst area, too lumpy to make a good mating surface. So my plan is to use these Delrin laser cut flanges and some type of urethane or sealant as basically a gap filler. Since my flanges are based off the CAD model, which didn't perfectly match reality, I filled in a few little gaps here with some expanding foam that cures hard, and I can sand smooth with the rest of the surface. And then I'm just gonna clean it up before I add the gasket tape. At this point, I used a jigsaw to cut out the decks after I traced the pattern from each hole independently onto the blank piece of plywood so that they would match up, and I added gasket tape. The gasket tape, 3/16 thick, is more than enough to take up any irregularity in the thickness from the flange and the fiberglass. And then once I have all my bolts match drilled and clamped into place, I'll come through and do a final sanding to get rid of any excess material and trim everything to be flush with each other. I've just match drilled through all my deck bolts, just kind of roughly evenly spaced in the nicer, flatter parts of the fiberglass. Next, I'm gonna pull the deck off, coat it in the waterproofing stuff, and check that the seal looks good still on the inside. I've made sure it is compressing the gasket all the way around. I put some weights in the holes, and I left them floating around a little while in a makeshift pool to do some leak checks. And at first, it definitely did take on some water, and it sank a little bit lower. I pulled it out and saw where the water was dripping out to find any of the leaks. The first hole that I built turned out to be much leakier than the second one, so this was kind of an iterative process of patching leaks, floating it again, taking it back out, looking for more leaks, more patching, etc. These pictures are from the second hole that turned out much cleaner than the first. Overall, I think the main thing I would do differently is I would try to use some kind of vacuum bag to squeeze out all the excess epoxy, which just made it heavier than it needed to be. The first completed hull assembly turned out to be around 14 pounds or so, and the second one, which I was able to do much better, turned out only to be about 9 or 10 pounds. But after I finished them, I spray painted them orange and added an extra layer of that white sealant on the inside to fill in any tiny little pinholes. In these side-by-side pictures, it's really obvious that the first one is so much lumpier than the second. I tested the solar charging assembly thoroughly on its own, measuring the current here that the panels were able to charge the batteries at. Using that clamp meter, it's about 4 amps in that cloudy day. There I have some load resistors to draw 12 amps off of the batteries and make sure that that charge controller could handle it. And I also tested drawing through the load resistors while charging from the panels at the same time to get a slightly net positive current on the battery. After I verified it was able to provide enough current and charge the batteries adequately, I started assembling the structure underneath the solar panel. Those are 2020 aluminum extrusions with some through bolts. Those bolts then go through some 3D printed mounts that have some captured lock nuts, and I set the assembly on top of the holes, looked underneath, and I added some shims here and there to get everything sitting level. There was a slight gap in a few spots, so I added a lot of weight on top while I was gluing. I traced where all the mounts go and then added the glue in those spots. It was a marine grade structural adhesive that secured those on. Specifically, it was 3M 5200 adhesive. I tested a small section on a thoroughly sanded 3D print with the same plywood, and it actually delaminated the plywood before the adhesive failed, so I was happy with it structurally. I let the whole thing cure a few days before refloating it here. Now that it had most of the weight in place, I wanted to check that the water level was sitting about where I expected it to be. With only the panels on, it was a little bit nose heavy, sitting a little bit low in the nose, which was expected without any weight in the back. But I measured it at all four corners to get an idea of being able to quantify how it was sitting. I even broke out the level in a few spots just to make double sure, and that gave me some insight on exactly where to place the batteries and the rest of the heavy components. I kind of could have placed those anywhere in the hull, so that served as a adjustment for the COG. I ended up placing them almost all the way in the back. There I was kind of pushing it back and forth to get a feel for how much drag there would be in the forward direction. And here I added some weights in the back to simulate placing the batteries and the other heavy electronics, and that leveled it out. I took it apart again, and I did one final leak check by filling both holes up to the brim with water and looking for anywhere that it dripped out. And I identified one or two more tiny little pinholes that I did a quick patch on. So by now I was confident that they wouldn't leak at all during the first actual run. I put the batteries most of the way into the back of the holes. These were kind of a no-name eBay lithium iron phosphate because it would be fairly fire safe, and with a continuous discharge current of 10 amps per battery, 20 total is a lot more than I would ever expect this to pull. They can also charge at 10 amps, which is more than the panels will provide. I printed a low drag enclosure for the echo sounder and filled in the voids with expanding foam to give it a little bit of buoyancy. That's a Robotics Ping 2. I resin printed most of the parts for the Rudder Servo assembly so that it would be resistant to deforming under the heat and UV from sun exposure, like a lot of FDM parts would. Plus I needed some fine resolution for the teeth on the smaller pulley, which I also resin printed. This design used a 2-to-1 reduction between the 180-degree servo and the rudder to get 90 degrees, 45 in each direction of rudder travel. I'm not totally happy with how the bearing setup worked out. This does not have a real bearing or bushing anywhere. It's just the threads of a through bolt going through the pulley printed part and rudder attachment point where there's a captured lock nut. So it's not clamped down, but there are some washers for spacing that let it ride as smoothly as reasonably possible, although I would like to upgrade to probably some kind of flanged bushing or a bearing at some point. This end just spins totally freely. It uses the same actual printed parts though, just so it's fewer parts I have to design, and they're swappable and reversible, and it's driven by a tie rod to the other end. This is the driven end, doing some testing with the integration of the servo and the drive motors into the whole setup. I've just had some successful bench testing of most of the electronics integrated except for the solar panels. I've got everything kind of loosely installed. The connections over here are the Rudder Servo, the 2 motors, the battery from the other hole. This big multi-conductor cable goes to the radio receiver, then USB port going to the laptop so I can flash code and read the values it's printing. Switch for the load, switch for the battery disconnect, the actual GPS antenna, which somehow is giving me a signal indoors in my garage here, and the sonar unit, which is not giving me anything meaningful sitting there on the hull, but I am reading data off of it. One of my props is spinning the wrong way, but I can easily fix that by swapping 2 wires. Other than that, the new code for the manual control is working pretty well. The logic is sound. The only things I've changed since the last version are the bidirectional ESCs and adding the rudder servos. The way I've got it set up in manual mode is to do rudder only until I hit 50% steering and then go into differential thrust. Pardon my incomplete cable management for testing purposes, but I wanted to walk through the wiring a little bit. I have 1 battery here. The terminals of the battery go into a little Y junction with this wire going out the deck and into the other battery. Each battery has an inline fuse. You might be able to barely see it right there. And then before that connection goes to the solar charge controller, it goes through this switch. So that lets me disconnect the batteries from the system. The positive lead for the load of the solar controller goes up through the other switch and then back down to this terminal block where it's distributed to a few things that run off the battery voltage, nominally 12.8. So that powers both ESCs through these connectors, 1 there, 1 there. The ESCs include a 5-volt regulator. So in their 3-pin servo connector lines, that's what powers 5-volt back to the main brain board. That 12-volt rail also powers this DC-DC converter, which steps the voltage down for the servo to 8 volts. This terminal block on the other side is just a ground. Everything in here has a common ground. The 3-phase wires from the ESCs go through these little bullet connectors so that I can easily disconnect and swap to change the spin direction. Those then go out the hole here through the deck and off to the motors. This big 10-pin wire goes to the radio receiver on the outside, and it's routed down here into the brain board. And the GPS is this little wire right here, which goes through an adapter, turns into this black wire, and out the hole through that hot glue because I didn't have a cable grip of the right size. And this one is the sonar module coming through the deck there. Under that heat shrink is some disconnectable connectors because I didn't want to cut this wire on the expensive part. And then it's soldered in there to this multi-conductor cable over to the brain board here. And next to the external GPS antenna, these are the solar panel connectors, which are not plugged in, which go up through the deck down directly into the solar charge controller. These 2 daughter boards, little breakout boards, are DC current sensors. So one has a line going through it, which is the load, and the other line going through the other one is the solar power. That interrupts the load line before it goes to this distribution block. So I'm measuring the total current draw of the motors, the servo, everything, including the brain board itself. And the last deck penetration is this cable. That is an external panel mount with a waterproof cover on it for a micro USB. And that goes straight into the Teensy microcontroller. That lets me flash code onto it without popping open the deck. And I'll have a separate program that lets me read the SD card straight from that. Also coming from the brain board here, routed all the way up to the bow, is my compass. And I've got that removed temporarily for testing so that I can spin it around without moving the entire boat and make sure I'm getting accurate readings. And that's all the way up in the front so that it's not near any kind of high current wires or the motors themselves to minimize any kind of interference. Everything in here is attached to the inside of the hull on some 3D printed mounts that are secured with some Velcro tape, so that lets it be kind of modular and I can remove individual parts and swap things out pretty easily. Here I'm testing the proportional control by wiggling the compass side to side and making sure the rudder responds in the correct direction, and playing with the gains a little bit to get it to what looks right. Turning it to the extreme there, the differential thrust kicks in as well. Now I'm testing the integral control. I just set the compass down with a very slight error between the actual heading and the goal heading, and you'll notice the rudder is gradually turning as the integral error builds up. In the autonomous driving mode, it only uses the rudders to steer when it's close to straight, and once the rudders have reached their hard stop, their full value of 45 degrees, it will then keep the rudder locked and gradually apply differential thrust from there, slowing down the inside prop and eventually reversing it. So in full turning, it can rotate on a dime in place. I have the derivative gain set to 0. The nature of the rotational drag in the water already kind of dampens this pretty heavily against sudden direction changes on the compass error. But I generally just kind of played with the proportional gain and the integral gain independently until they seemed about right based on what I could test in air, but further tuning is definitely going to be needed once it's in the water. One last peek at the wiring before I button all this up. Got everything tied away so nothing can rattle around. Got all of my signal lines routed as best as possible away from any high current power lines. The DuPont headers over here, I just gave a dab of hot glue to prevent any vibration from shaking those loose. I cut the tie rod to length and installed it in place. It's just an aluminum tube from the hardware store with some threaded inserts. One's left hand, one's right hand, so I can rotate it to finally adjust the length and lock it down with a jam nut. The boat was pretty much complete at this point, so I put it in the pool one more time to do a load test on the motors, the rudder servo, and everything else. Full system integration, running under its own solar power, and logging data with its own internal sensors. I was mostly controlling it manually here, changing the throttle between full forward, full reverse, and turning the rudder hard side to side, just putting it under the most stress as possible on the power system, making sure there's no current spikes so high that it causes a brownout or anything like that. The only issue I ran into was the rudder servo belt skipping, and I think that was because there's just enough flex in the system that under a sudden direction change under load, it can jump a few teeth on the small pulley. So before my first lake test, I reprinted that servo mount a couple of times to get more travel in the belt tension adjustment, but unfortunately the belt skipping was still a little bit of an issue, even when I had that belt as tight as I could, so I'll be moving away from that design in favor of some kind of push rod linkage. This is a close-up of that belt skipping. I did adjust the tie rod position to prevent a collision between it and the pulley at the extreme of the travel, but that didn't entirely solve the problem. I built this trailer for moving and launching the boat out of just old junk I had laying around. That main frame is actually from an old treadmill I got for free and took apart for its motor. Just a nice sturdy steel rectangle that would sink. I cut up some lumber to build a little subframe to mount the wheels to and make an attachment point at the front. Also a pull handle. The wheels themselves are from actually an old pressure washer, just bolted right on. They're non-pneumatic, although they actually did still trap some air inside that caused the front end to float a little bit designed it to just barely fit in my truck bed. And that's the fully assembled trailer, giving it the classic sturdy weight test, and it had some 3D printed parts to attach the boat and some V shapes that went underneath the hulls with some soft Velcro so that it could slide back and forth a little bit once it's launched. This is the reprinted servo mount just to get the belt as tight as possible before launch, thinking that would solve the belt skipping issues. Once the whole assembled setup got the seal of approval from my quality control manager here, I was ready for launch. Forward. Oh yeah, it's faster than I even hoped. Alright, here goes. Automatic mode. Oh my god, it's working.
Wow, that's really fast.
That's faster than I thought. Okay, wow, that's perfect. The plan here was for the boat to follow a predetermined coordinate path that was the same as one I'd done before on the previous iteration. But there was a bug in my new code, unfortunately, that caused it not to read the GPS data fast enough. So it failed to detect when it had reached a waypoint, and it just kept following the same goal heading. So rather than kind of zigzagging across the lake like it was supposed to, it just picked a heading, followed it for several minutes, and only updated the heading once every 10 minutes or so. So a few times I went out and paddled up next to it and manually hard reset it, and that updated its GPS coordinates every time and picked a new heading from there. So rather than doing a fully autonomous mode, I did a few short stretches of auto mode and a lot of manual testing mixed in. The code running during this mission was only reading 1 byte of data from the GPS every loop of the main loop, and that was not enough to adequately update the latitude and longitude to recalculate the goal heading quickly. I did not catch that during my bench testing because the boat was stationary in my yard or my garage, and I just didn't expect the GPS latitude and longitude to change much, but I will definitely fix that bug before I upload this code to GitHub or something. Although it couldn't exactly follow the predetermined coordinate path like I had planned for, this test was still really useful in validating the PID control that it was working as expected. The new hull design performed okay in the handling. The rudder geometry worked out nicely for turning it sharply and for making fine adjustments in a straight line. The differential thrust worked nicely for turning in place when needed. And it even has reverse, which is a big upgrade over the last one. I collected tons of useful data from this mission that'll help me to optimize things in the future, and I got a lot of cool footage too that I'll put together. Some of these clips are going to be sped up just for the sake of brevity, but it should be obvious which ones are in real time and which ones are not. So hopefully I can show off some of the performance of this boat and demonstrate some of the data I collected too. Here's the boat being immediately flipped into auto mode, then calculating a goal heading and steering towards it. You might notice at the beginning it did use differential thrust, which is a little bit hard to tell the prop speed based on the camera frame rate, but it pretty quickly settles into its goal heading and maintains a nice straight line, tracking pretty well, not doing any crazy S-turns. This was a beautiful, calm day. I almost wish it were a little bit windier so that I could test how it performs going against the wind. But I should note that a lot of this was filmed from a moving kayak, which makes it a little bit hard to tell sometimes how fast it's going. It is quite a bit faster than the last boat though, for sure. There were a few cases during the run where the belt skipped a little bit and caused the rudders to be stuck a little over to one side. Even when that was fairly extreme, I actually was still able to steer the boat straight by giving it more steering input to the point that it started using differential thrust, and it was still able to go straight, although at a little bit of a slower pace with one motor slowed significantly. Also in auto mode, the integral portion of the PID control was successfully able to account for the rudder being a little bit offset in cases where the belt had skipped, and it was still able to straighten out. I made these plots using MATLAB based off of the raw data collected during the mission. This top plot is the actual heading versus the goal heading. The goal is these orange lines, that's the compass heading in degrees that it calculates to reach its waypoint, and the blue dots are the actual heading that the compass is reading in that exact moment in time. So this is essentially a step input to the PID loop, and in most cases, starting with a slight offset, it pretty quickly settled to the goal and maintained a close match to the goal pretty well. If it started really far off, it did tend to overshoot a little bit, and that tells me that maybe I should decrease the proportional gain a little bit. But overall, it worked pretty well. In most cases, it did slightly overshoot, correct, and match the goal heading pretty closely. Notice here, actually 0 degrees, when it reaches 360, it loops back around, so that's what's going on there. And also I did cut out all of the data where it was running in manual mode, so what you see here is purely stretches of auto mode following a waypoint. And since the GPS was not updating quickly enough, this goal heading stayed the same for most of these runs. Once I fix that bug, the goal heading itself will be slightly changing as it recalculates the target if the wind starts pushing it off course or something. And now this lower chart is just the raw PID output from minus to plus 100. That's essentially, you can think of that as the steering input, like 100 being as hard a left turn as you can, minus 100 being as hard a right turn as you can. So on this first run, it started with a bit of a turn and then nicely settled into a pretty much straight 0. And then notice that some of these other runs, it settled into a different value that was in some cases far from 0. And that happened because the belt slipped a few times, causing the rudders to be a little bit offset. But the integral portion actually did account for that, and it reached an equilibrium value, keeping the servo slightly turned to one side or the other. It struggled a little bit in this section, essentially bouncing off of the maximum output, steering as hard as it could, and you'll notice it struggled to maintain a straight match with the goal there. In that case, the rudder was just turned over so much that it had a hard time accounting for it with. This chart shows the raw PWM values being sent to both of the forward thrust motors and to the rudder servo. So the thrust motors, in most cases, it started out in auto mode with a little bit of an offset heading from its goal, and one motor was initially throttled back. In this case, 1500 is 0, lower than that is reverse, and 2000 is full forward speed ahead. So in these cases where it followed a nice straight line, both motors were pretty much just pegged at 100%, and all of the steering was making fine adjustments with the rudder in which case 1500 is 0 straight ahead, and the extremes are at 45 degrees. So in the highly offset cases, it would start out with one motor all the way in reverse, and it would settle into both being full throttle forward. This one area here where it had trouble, you can see it was maintaining its heading with differential thrust. The port motor never quite got up to 100% there, and in that case the rudder was pegged all the way over. Again, the way my auto mode works is it uses only rudder for fine steering adjustments until the rudder reaches the end of its travel, and then it starts linearly applying differential thrust from there. This chart is to compare the current produced by the solar panel and consumed by the whole system. So the black line, which is nearly at a consistent, more or less 13-14 amps throughout the whole time, is the current going into the charge controller from the panels. These dips here and there and this long period where it was stuck in a tree are all when it was temporarily out of the sunshine, clouds passing over, etc. And then the blue line is the consumption from the system, mostly pegged at nearly more or less 15 amps. That's when it was in full throttle going forward with both motors. Some dips here and there when I paused the boat and it was nearly at 0, or when it steered in such a way that one motor was throttled back. And then the green line is the net into or out of the battery, positive being current going into the battery, negative being current coming out of the battery. And for most of these long straight sections, I was slightly in the negative, pulling around 2.5 amps from the battery. So if the conditions were better and it were perfectly sunny, I'd probably be right around a 1-to-1 consumption to production ratio. But combined with 20 amp hours of battery capacity, even if it's slightly underperforming the consumption, this thing will be able to run all day, no problem. A 2 amp deficit gives me 10 hours on the battery capacity. In the lower chart is the battery voltage. Right at the beginning, it was sitting there on the land, turned on but not doing anything. Slowly charging, the battery voltage increased. It started a little bit low. This is nominally a 12.8 battery, lithium iron phosphate, so it tops out at like 14.4 or something. And then we have some pretty big voltage drops when the motors kick on and are running, and that varies depending on motor throttle and such. But by the end, when it settled out again, it was actually slightly above where it started at around 14.4, so pretty close to full. Even though it was at a deficit in charging in some of these cases, it did spend a lot of time with the net being positive if it was just sitting there stationary, and it can provide quite a bit of current into the battery. One interesting note about this region, right before I sent it on its way and it started drawing a lot of current from the motors actually being on, the consumption was essentially 0. It was sitting on land, slowly charging at a low current because it was in partial shade. And then I think what happened here is the internal BMS kicked in, or the charge controller itself has a voltage cutoff. But either way, the battery reached its nominal maximum voltage, and then the system started throttling back the charging current. So there's some points in here where it's mostly at 0, and then it quickly goes up for a brief instant and then goes back down to 0. And then once I sent it on its way, the voltage started dropping significantly and the draw was higher. Then it allowed more current through from the solar charging current actually. Those internal BMSs and the solar charge controller each have a low voltage cutoff as well, which did not go into effect at any point here because it's around 10.5 volts. But I do have redundant mechanisms to prevent both overcharging and over discharging that seem to be working as I expect them. I had an onboard camera filming this entire time. Here's a randomly cool clip of a bird that happened to fly by. this is some of the raw black box data as an example. This first number is the time in seconds since startup, and you can see these numbers, the latitude and longitude, are not updating until that time resets, which is when I flipped the switch and did a hard reset, and then it updated. So that was due to a software bug. The rest of my data is updating adequately in real time. The goal heading also not changing because the latitude and longitude are not changing, but I got good actual heading values, heading, error, current, voltage, so forth, PWM signals. Consequently, my error log is full of this GPS lost error. I was getting good depth data this whole time, these values between 2, 3, 4, 5, 6 meters or so. But without the GPS coordinates updating often enough, I can't really make a meaningful depth plot out of this. Overall, I'm really happy with how this first real test went. It was mainly intended to be kind of a shakedown run, not necessarily going for a full-blown depth plotting autonomous mission on the first iteration after this complete redesign of the boat. But I only had one minor software bug and one minor hardware bug, being the GPS signal and the Rudder Servo belt. Both of those are pretty easily fixable, and I'm glad that I was able to validate all the more critical design changes and improvements, the new hulls, the rudder steering system in general, the PID control, etc. So once I've had a little more time to make some improvements in those areas, I'll be back for a more thorough mission in probably a new location to do some real depth plotting. So in the meantime, thank you for watching.